Swayam Prabha. Digital India. Educated India.
Okay, today we'll be talking about robot specifications and robot programming. So in the last class, what we looked at is the control systems and how to design a very simple PD controller and a PID controller which can take the robot link from some position to some other position in some time t. Okay, so today what we are looking at is robot programming. So most of the industrial manipulators or the manufacturing companies would provide a very simple programming language by which the user can actually program the robot and then use the robot. Okay, so first we'll talk about robot specifications and then we'll talk about robot programming. So in the last class, to revise very quickly, what we talked about is that the basic control system has 4 parts. One is the controller. The second part is the actuator, which is the motor in our case. So we have an actuator here. Then we have the actual link of the robot which is moving in space, and then we have a position sensor which is a position sensor like an encoder, and this is my closed loop control system which controls the link of the robot. So in the last class we also said that essentially if you look at the dynamic equations, the dynamic equation tells us that the joints are all coupled with one another, and because of which the effect of one motion of one joint comes on every other joint. That means every joint affects every other joint in the system, and this is what we call by a coupled system. So in reality a robotic system is a nonlinear coupled differential equation, the equation of motion, and this basically says that the system is coupled in nature. But controlling a nonlinear coupled system like that would be very difficult. So what we do is we simplify it and then consider every joint to be independent, and then each joint is not only independent but it is actuated by a single motor, gear and an encoder. Okay, and we make the assumption that it's a linear control system. Okay, so this is what we did in the last class. So in this control system what we have is an actuator which is a DC motor in our case, so DC motor here, and then we have an position sensor which is basically an encoder. So we also discussed what is an encoder. So this is how an encoder works, and it basically has an emitter and a receiver pair, and when light is going through or light is not going through, you get a signal of 0 or you get a signal of 1. That is how the encoder essentially measures position, velocity and acceleration. So using an encoder, the position control, the feedback control system can get the position, velocity and the acceleration. And then we also explain the working of a DC motor. You are all familiar with the working of a DC motor. We give a voltage to the brushes here, and then this voltage passes through the coils producing a magnetic field, and because of which that magnetic field interacts with the magnetic field of the permanent magnet which is here, and as a result there is a net torque on the system or a net moment due to which it rotates. Now what we looked at further in terms of the control system is that our equation of motion comes out something like this. Okay, so which consists of the inertia part, it consists of the Coriolis centrifugal part and the gravity part. So in reality a robot control system is a multi-input multi-output system, but we simplify it by saying that this is an independent joint control. That means every joint consists of a motor, gear and an encoder, and we also say that this is a single input single output system. So based on that, what we saw in the last class is we can design a very simple control system. We can first of all model this system as a linear control system, as a linear control problem, and this is essentially an approximate method in which we say that every joint is consisting of a mass, a spring and a damper, and then we write our equation of motion like this. And then so this contains the inertia part, this contains the damping part, and this contains the spring part, the stiffness part. And we model it like this, and why do we model it like this is essentially because we understand that how the system would behave. So the characteristic motion of this equation would depend on the values of m, b and k. So the characteristic equation, if we solve, we can solve it, and then we will get 2 roots of the equation, and the 2 roots of the equation basically determine how the system will behave. For example, it is going to be overdamped, we saw it will be critically damped, or it is going to be underdamped. So, based on that we can design our control system to behave in a particular way, and we say that we basically want critical damping, which means B squared is equal to 4 mk. So, this is the condition for critical damping. So, our system is going to behave with very little oscillation here and it will come to rest like that. Okay. So, this is basically showing some kind of critical damping behavior. So, doing this, what we can do is we design a control system and then choosing a value of Kp and choosing a and critical damping. So, first condition is Kp, you take some numerical value, then critical damping. Critical damping means B squared is equal to 4 mk. So, from here we can basically find the value of the other values of Kp and Kd, and then design our position regulator or a tracking controller. The basic difference being a position regulator essentially keeps the position in the desired location. So, for example, if this is my spring mass damper and I disturb it a little bit here, now the controller will tend to bring it back and keep it wherever it was. So, it just maintains the position. So, that is a position regulator, whereas a tracking controller is the one that tracks a trajectory. And then we what the basic difference between them is that in a tracking controller we generate an error and then we try and make the error equal to 0. Okay, that is the fundamental difference in a tracking controller, whereas in a position regulator we just try to keep it at the position. Now, moving further, what we discussed in the last class, if we write our the actual equation of the actual system, then what happens is you have a motor on one side. So, this is my motor which is generating a torque tau m, and there is a gear in between the motor and the link, and there is a link on the other side. So, essentially whatever motor torque is being generated is rotating the motor, this is the rotor of the motor, and it is overcoming the friction, and then the speed of the motor is getting reduced by the gear ratio. So, this is my gear ratio, and then it is going on to this side. So, it is coming from this side, speed is getting reduced, it is going to the other side, which is the link side. And so, the function of the gear ratio is to decrease the speed and to increase the torque, and so our equation relating the motor angle theta m to the motor to the link angle theta L is equal to 1 by zeta into theta L, right. So, this gives us the relationship of the angle, this gives the relationship of the joint velocities, and this gives the acceleration. So, if you write our equation, then what will happen, the torque equation, then basically the torque that is being produced here is getting consumed or is moving the motor rotor, is overcoming the motor friction, then it is going on the other side, going on the other side, and it is multiplying and it is moving the link on this side, link inertia and the link damping. Okay. So, this is the total work that the motor torque is actually doing. Now, if we convert everything to theta L, that means I simply replace theta L by theta m from using these equations, and what we get is this equation here. Now, I combine all the theta m double dots to be here, and then I get this term. Similarly, I combine all theta m dot, and what I get is, so this theta m dot. So, what we get is this equation, right. So, basically what we see here is that the zeta squared comes in the denominator of this term, which essentially means that now this is very, very important, as I explained in the last class, that a robot, unlike any other control system, a robot picks up some weight and then it leaves some weight. So, essentially the mass of the end effector is going to change. The moment it picks up weight, it becomes, the weight goes up, the mass goes up, and the moment it leaves the weight, what happens, it drops the object rather, what would happen, the weight will come down. So, what happens is the end effector has a different a variable mass now. So, you know that for tuning a PD controller, if you change the mass, then the tune values do not hold anymore. So, but what we see at the other side here is that when the robot picks up a load, that means the JL is the link inertia plus the object weight. This object weight gets reduced by the square of the gear ratio. Okay. So, it essentially means that we have a link which is the link inertia for the link plus that of the object which is lifting. So, this is the object which is lifted. Okay. So, this object lifted can be, if nothing is lifted, it is 0. The moment something is lifted, it becomes a particular weight, it has that particular weight. So, essentially this full JL term is going to vary, it will have the link plus this or the object or no object, but this full is getting divided by zeta squared, which essentially means that if you have a high gear ratio, the change due to the object being held or not held is divided by a very large number, which is the square of the gear ratio, and the result of that is that the effect of the object being held or not held is not reflected onto the motor, and that is the reason why once a PD controller is tuned, okay, for a particular mass, the mass is normally tau L, but even then that same tuning actually works even when the robot picks up an object, because the object weight is not felt by the controller. So this is something very, very important that we need to keep in mind, that when we are designing a control system or we are tuning a control system, or rather when we are actually designing a control system, it basically means that you should not use only a motor, you should use a motor with a gear ratio. Otherwise what will happen is the effect of the change in the object weight will start getting reflected on the control system, and it will go out of order, it will not be in sync anymore. So this is an important result showing the importance of the gear and the motor. So if you go back here again, we said that the independent joint control, this is an independent joint control, has one block or one unit, and each of these units consists of a motor, and you would see that there is a gear in front, okay, and then there is an encoder at the back. So there is a particular reason why it is designed like this, okay. So essentially the motor is going to get connected to the gear and it is going to go to the joint. So if there is a mass here, so there is an mg weight which is being picked up or dropped, this effect of this does not come onto the motor because there is a gear here, okay, and so the effect of this will get divided by zeta squared, okay, and if you have a very high gear ratio, what would happen is the effect will not come. So this is something to remember. Now a couple of other points we need to remember before we move on to today, that is robot specifications. The first thing is that when we looked at the encoder, okay, so here we have a gear, okay, you know what's a gear, there is a motor, DC motor, there is an encoder at the back. Now if you look at an encoder, what we see is that the way it works is, if I enlarge this a little bit here, okay, so there are slots like this, okay, so there are slots like this. So if I just take and enlarge it there, so essentially in this slots basically the light will go through here, so it will be 1, light will not go through here, it will be 0, so it will be 1 0. But if you see that there is a distance here, from here to here there is a distance, there is some distance there, which will mean that the encoder between here to here, for every position between here to here, it will simply say it is 0, okay. That means it cannot actually distinguish any position inside here, okay, that is what it means. So it can read this position, the next position it can read is this, and in between here to here it is blind, it can't read anything. Now this basically means that there is something called a control resolution now. That means as far as the control system is considered, let us move on to the robot specifications. How do we specify a robotic system? So in terms of the resolution, these are three terms that are used. Resolution, so resolution is called the smallest unit the end effector can be positioned in space, and this is essentially called my control resolution. Now the control resolution essentially would be because of one of the parameters is that in the memory of the robot, okay, there is a finite number of storage, or the memory of the robot can only store a particular in a particular sequence depending on the number of bits it has. For example, if you look in the case of a scale, okay, just to give the example of a control resolution, so this is my scale, you are familiar with the scale. So the scale has a 0, then it has if I am just measuring and enlarging this, suppose this is my 1, this is 10, this is 20 in millimeters, so this is 5, okay. Now this is 1 2 3 4 5, again 1 2 3 4 and 5, okay. So in this scale, when you are measuring in centimeters or you are measuring millimeters, so you cannot measure something which is in between. So if I enlarge this part now, okay, I am enlarging it here. So what I am trying to say is that if this is my 0 and the next one is coming here and the next one is coming here, okay, and this is my 1 2 3 4 5, this is my 5, I enlarge, then what is basically I am trying to say is that essentially any point here you cannot measure, because you can measure here, you can measure here, you can measure here, but you cannot measure in between there, okay. This you would have noticed in a scale. For example, if I say 10.1 millimeter you can measure, but if I say 10.05 millimeters you can't measure, because you are going in between now, okay. So similarly in a control system, in this control resolution of the system, what we are basically seeing is depending on the storage in the memory. So whatever is the storage memory size of the robot controller, suppose it is a 12-bit storage, okay, then it can store only a finite number of numbers, a finite number of digits. So if it is 12 bits, then this 12-bit system can be divided into 4096 units, That means whatever is the range of the robot. For example, the robot arm can move by 1 meter. So this 1 meter has to be stored in 4096 units or 4096 divisions, which will basically mean that 1 by 4096 is 0.244 millimeters. So it basically means that the robot cannot distinguish anywhere which is lower than this. Okay. Why? Because it cannot be stored in the memory, that number cannot be stored in the memory. So we can have something like this. We have 2044, and the next one is going to be 488, 0.488 is the next one in that order. So you cannot have anything inside here. Okay. Suppose I want to ask the robot to go to 0.256, it cannot go because this fellow is not in the memory of the robot anymore. Okay. Because it's a 12-bit storage. Okay. So this is what essentially causes what we call the control resolution, that in terms of the control system, okay, and the memory size of the robot, depending on the number of bits it can store in the memory, the total range of the robot will be divided by the number of bits, and that is going to decide the smallest number where it can go to. So if I were to draw it here, if I draw let us say this is my scale, okay, so the robot can go to this point, it 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 cannot go anywhere in between. Okay. So in terms of control resolution, these are points where the robot can go to, and these are defined by the number of bits it can store in its memory. Okay. So this is essentially called control resolution. Now we have again seen that the control resolution depends on the number of bits in memory. So bits in memory, whether it's a 12-bit system, it's a 16-bit system, it is 32 or 64, depending on how many access points it can take. So this is the first term that we are seeing, that is resolution. So it basically means that the robot cannot go to every point in space, right. So it can go in between 2 points which are decided by the control resolution. Now in terms of accuracy of the robot, we see there is another term which is called accuracy. Now accuracy basically means the closest the robot can position to a desired point. Now what is the desired point? The desired point as I drew here is here. This is my desired point. Okay, so this is my desired point, okay, where I want to go. But what would happen is, because there are other terms which are coming in, for example, one is my encoder finite points. This is something we discussed some time back, that we have an encoder, and an encoder you can go only here or you can go here. In between you can't define it, so in between it is blind. Okay. So if I want to actually go to this point, I actually cannot, because I cannot read that point as far as the control system is considered. So because of which the encoder can actually go to finite number of points only. Okay. Now, so this is one. The second is, there is a lot of gear sitting there. We said that there is a motor, there is a gear. So there are things like gears. Gears have backlash. Okay. So backlash basically means that the gear teeth are not exactly in mesh, there is a little bit of gap in between. So when it moves on one side, it will move, and when it goes backward, there will be a slight lag of the motion there, and that is what is called backlash. There can be other errors like mechanical stiffness. So mechanical stiffness can be there because this is not a rigid body, so there is going to be something which is slightly which is going to slightly deflect, which is going to cause some kind of mechanical stiffness errors, and all these fellows combined will add up and will finally end up ensuring that if you want to go to this desired point. So I wanted to go to this point, but what has happened is I have actually ended up going there. Why? Because these errors here are because of all these points here. So whatever we have said here, let me draw it here. So all these 3 points here that I have written will cause these errors here now. So it will go this side or it will go this side. Okay. So this distance is my accuracy. So first of all we defined what is my resolution. So this is my resolution. Okay. So this is my resolution, which is essentially because of the controller being able to address only finite number of bits. So if this is my resolution here, here and here, and so theoretically I can go here because it is accessible in the controller, but when I try to go there, this encoder has some finite points it can access. So finite let us call it access points because it is digital, and then there is something called gear backlash, then there are mechanical stiffnesses, there can be other errors in the system. For example, there is some amount of play. What I mean is the play basically means when we are fitting two parts that is not tightly fitted. So there is some kind of looseness in there. Okay, these are normally mechanical stiffness and mechanical errors. It can vary because of temperature, okay, wear and tear, etc. Okay, so all these fellows will add up and ensure that if you want to act. So in the controller, if you want to go to this point, what will actually happen is you will end up at this point or you will end up at that point. Okay, so you will not exactly be able to go there, and that is what we call our accuracy. So the closest the robot can position to a desired point is called the accuracy of the system. Okay, the accuracy of the robotic system, and you should be aware of why it happens. Okay, it is essentially because of the other errors which are sitting there. Now we have seen in terms of definition that if I want to go to this point, I can come from this side or I can come from this side, right. So this is in 3-dimensional space. I can actually come from any side. Okay, if it is 3D, you can imagine I have drawn it in 2D, so it is being shown as a line. So essentially it can come from this side or it can come from this side, which means that if you are trying to define it, then the accuracy is defined as half the resolution. So accuracy is equal to half the resolution. Okay, so if this is my resolution, then half of that is my accuracy, which is this side and this side. What is the logic? The logic being that you can come to this point from the right side or the left side. So essentially it is half of which, so half of which if you measure, so half of this is equal to this much. Okay, so half of what? Half of this. If this is my resolution R, then half of that is this much, so you can come either from the right side or you can come from the left side, and that is how it comes to half of the control resolution. Okay, so this brings us to the second term, which is accuracy. So accuracy is given by half of the resolution or the control resolution. Now there is one more term. So we have seen two terms. One is the resolution of the system, the second is the accuracy of the system, third is the repeatability of a system. Now a robotic system will actually do work in space. Essentially it will be accessing different points. Say for example, I want to pick up this object from here and I want to keep it here. Okay, so when I want to pick up and keep an object repeatedly, okay, so this point, this object is coming here, I want to pick it up from here and keep it here. Now I want to do this repeatedly. How many times? Very large number of times, maybe 10 million or 20 million cycles, 20 million times. Now it basically would mean that can I come to this point all the time, or repeatedly do I come to exactly the same point, or is there an error there? Okay, now in terms of this line that I have drawn, it would appear that you can go to this point, this point, this point, because they are addressable in the control as far as the control system or the memory is considered. But what we see is that when we try to go to that point, this it will not go to this point here, but it will start, it will not go exactly there, but because of this term called accuracy, it is going to go somewhere here. Okay, so that is the region it is going to go. Okay, so now if I say if I want to go from this side or I want to go from this side, and if you can imagine 3-dimensional space, I can also go from this side and this side. I can come from any side. It's a 3-dimensional space. Now all these errors that are there are going to start. These errors are going to be different in different sides from different sides. So if you understand what I'm saying, the error from this side would be different from the error from that side. Okay, because these parameters again are directional parameters, right? So what would happen is, and some of this like wear and tear will start changing with time. Okay, so all this added up will make it a system in which, suppose in the first time I have been able to come to this point. Let me explain it this way, that in the first time I have been able to come, I want to go to this point, this is my desired, okay, but I have not been able to go there, but I have been able to go there. So this is my taut point. So this is my taut point. What is the meaning of taut point? It basically means that I have taught it the robot to go to this point. It could not come here because of all these other elements. It ended up coming here. Okay, but now then, so this is my first time. Now the next time, if I wanted to repeatedly go to this point, what you will find that it will not go here. It will go somewhere near here. Okay, it will go into some region which is near there. Why? Because the errors would depend on the direction in which it is going here now. So if I want to come to this point, this is my point. Okay, this is my resolution. So this is my resolution. Okay, so I have come here. This is my taut point. Okay, so I am able to go to this point. That's the meaning of the word taut point. I wanted to go here, but I have come here. Now repeatedly when I try and do this, I want to go to this point in, if you can imagine, in different directions. Okay. What would happen is at all these different locations it can come in some point here, it can come some point there. Okay. So this fellow will actually go and sit on any side of this point. So what we finally ended up with is this points where the robot end effector is actually coming. So theoretically I should have come here, but what is happening is, because these errors are directional, okay, and some of these errors are going to change with time. So what would happen is I will end up with a region in space about which I am coming. Okay. So this will actually come here. Okay. So what would happen is I end up with a region in space. So this is the region in space in which all the points are going to come when I try to access this point in all different directions, and that is essentially what is called my repeatability. So repeatability of a robotic system essentially means the ability, as given here, ability to position at a pre-taught point a large number of times. Okay. So in this particular case that I just drew here, this is my pre-taught point. I wanted to go here, but in the process I went here for the first time. So pre-taught point first time. Okay. Now I want to repeatedly go to point. Okay. What will happen is I will not be able to go to this point because I am coming in different directions. So what I'll get is there will be a region in space in which I will be able to go. Okay. So essentially this is what is called the repeatability of the system, and this essentially happens because the errors, a lot of the errors that we have here are directional errors, then they vary, varying errors are there, and the varying with all kinds of things like time. Okay. It varies with temperature, it varies with lubrication, then friction, etc., etc. So these fellows will ensure that the robot will actually never be able to come to the point where it went first time, but it will come somewhere near there. Okay. And this is basically what the third term that we call as repeatability. So in terms of specifying a robot, the manufacturer of a robot will be specifying all these three numbers. First is what is the resolution of the system, what is the smallest unit it is able to go. The second is what is the accuracy of the system, what is the closest the robot would go to a desired position, and that is normally defined as half the accuracy is half the control resolution. And then they will also give you a term which is repeatability, which says that if you are able to teach it once in space, but you want to repeatedly go to that point, what would happen is you will go somewhere near that point, and that is because there are different errors which are directional and dependent on other parameters. Okay. So these 3 points make up the specifications of a robot, and it is extremely difficult to find this one. Okay. Control resolution is fine because you can calculate this. So this can be calculated. So this can be calculated as we have calculated here. You have you know the bits in the memory, you know the total range of the robot, you can divide this by the bits in storage, and you know what is your resolution. Now you can also calculate the accuracy of the system because it is half the resolution. So this can be calculated. Okay. But it is not possible to calculate this one because these errors that are coming, okay, cannot be calculated. It is extremely difficult to calculate these errors. So the robot manufacturer will actually have to experimentally evaluate this. So repeatability is experimentally evaluated. So this is experiment to evaluate this error, and it is statistically found. It is extremely difficult. Why? Because measuring any position and angle in 3-dimensional space is very difficult. So if I say in this space at a point, suppose I say at this point I am able to take the end effector and I want to measure the errors that are going to come. So first time I take it here, the second time I take it, it does not go here but goes very near, but I need to measure the distances, and that is very difficult in 3-dimensional space. Okay. I need 3 coordinates of 2 points plus the angles. So I need to measure all of this, and that takes a lot of time and it takes a lot of effort. So what they do in robotics companies is they normally divide this repeatability measurements in planes. For example, if you can imagine, there is a wall on this side and there is a wall on this side. So if I hold a laser and I point, okay, then what would happen, the laser point will go and hit the wall. So what we indirectly measure is the laser point and how that is moving, and using transformations I know exactly where my end effector is. So using that they actually find out experimentally what is the errors that are coming. Then they find the standard deviation of the errors and then say that this is the standard deviation, this is my 3 sigma, and that is the repeatability of the system. And this takes time. It takes time because this error, some of these errors also depend on time. Things like wear and tear depend on time. So the manufacturer has to give all these numbers, and the robot specifications are normally given for the life of the robot, which can be 5 years, or it can be even more than that. So which basically means that these numbers will hold for 5 years, whatever the robot is doing. So this is basically called the robot specifications, okay, and we should understand very clearly what these terms mean, and in terms of how do they get it, and why these terms are there in the first place. Okay. So what we are saying here is that, so next is what we move on to is the evolution of the robotics technology and programming. Why? Because if a manufacturer makes a robot and the person using the robot has to actually learn control systems and do all the transformations, inverse kinematics, forward kinematics, probably nobody is going to learn, nobody is going to buy a robot, right. So it is not very easy to understand how the actual control system is actually made in the case of a robot. For example, are they using PD controllers, are they using PID controllers, what are the gains, that the manufacturers don't tell. Okay. So essentially, so the manufacturers must provide a very simple programming language, okay, either a programming language or an animation based something like a GUI, where you can actually use your mouse and move the robot around, and the robot can learn by itself. Okay. So that is basically a robot programming language, and we will see the evolution of one is the robotics technology and the other is programming. So robotics technology has evolved essentially from the very early days. So this is about 1950 or 1950s, where the microprocessor was first developed, and then we had robotics being made, and we also had NC machines, right. So NC machines and robotics, which I had explained in the early classes, is more or less the same kind of control structure, and they come from the same technology. And the essential the feature was that we had a program which was controlling a computer. So the machine control unit is basically a computer here, which was controlling a machine tool. In this case, it's an NC machine. Now this can also be a robot, it's exactly the same. So in the early days, 1950s, this was the basic structure. One program was controlling, was being run on a computer which was controlling a machine. Now as time progressed, we had the computer becoming more and more powerful, and 1960s and 70s, what we had is one single computer controlling many machines. So there is a bulk memory, and which contains all the programs, many programs together, and the computer can control many machines at the same time. So this is essentially because computer became more and more powerful. So essentially because computer became more powerful in terms of the memory size, in terms of being ability to run several programs simultaneously, etc., etc. So we have one computer, one machine, we have one computer, many machines. Then further progress, about 1980s, we have what we call flexible manufacturing systems. Okay, so this is about 1960s, 1970s to 80s is flexible manufacturing systems, which is called FMS. Okay, here what we have is one computer maybe. Okay, so this is a PC, or let's not say PC, let's say computer, controlling not only one machine but controlling different kinds of machines. So a computer is controlling different machines. Okay, so what are the different machines? So here we have a machine tool, it can be a lathe, NC machine, whatever. Then we have another machine work table, which can be a different kind of machine. Okay, this is a robot, which is not a machine tool, it's a robot. Then we have parts arrival, parts carousel. So the computer is actually controlling different kinds of machines now. Now if you are controlling different kinds of machines, what is required also is some kind of communication between the machines. Okay, so this is a requirement for different types of machines to communicate now. Okay, so not only must the computer control, what I mean by control is it should be able to move the robot to do some task. For example, the robot should pick up the part from here and then put it there. Okay, so the computer should be able to control the robot to do that. But There should be some kind of communication between the machines also now, okay, between here, between there, and between this and that. Why the need for this communication? Essentially because you can see from here and understand very easily that when the parts are moving, okay, this carousel is moving, okay. So when the part comes, there has to be some sensor there which will sense that the part has come. Now the sensor, once it senses that the part has come, it should stop the carousel, because the robot cannot pick up a moving object. So the sensor senses that a part has come, it stops the carousel. Now after stopping the carousel, it has to actually inform the robot that the part has come. Now you go and pick it up. So once the robot gets the information that the part has come, then the robot will go and pick it up. So the robot picks it up and then puts it onto this table, into this work table here. Now after the robot picks it up, it has to again inform the parts carousel that I have picked it up, so the parts carousel can start again, okay. So the parts carousel starts rotating and the next part comes there. Now after the robot has picked it up here and put it here, okay, the robot has to move for the wait for the next part. Again the next part comes and the carousel informs the robot that the next part has come. So the robot picks up the next part and puts it here. Again after picking it up, informs that the part has come, okay. So after the part has come, the carousel stops, informs the robot picks up this part, puts it there, and informs the carousel that the part has been taken up, okay. Now if you watch here, something very interesting is that there is one part here, so this one part here, there is another part here, okay. Now if the robot picks up a third part, what will happen is it will get what is called deadlocked, okay. There is a term called deadlock. Why? Because a part is here, a part is here. Now the robot has picked up one more part and it can't keep it here, nor can it keep it there, nor can it take out the parts from here, okay. So if the sequence of operation was, this was my first sequence, this is my second operation, and suppose after the machining is over, the robot has to pick it up and drop it somewhere, maybe here, okay. There is a bin in here, so the robot has to pick up the part from here and keep it there, pick up the part from here, keep it there, okay. So now if there is a part here, there is a part here, and the robot also picks up a part, what would happen is now the robot cannot pick up any parts from here and put it there, because the end effector is blocked now, okay. So this is what is essentially called deadlocking, okay. So what this basically means is that there is a sequence in which the operation is happening and it can get locked at some point. So the logic in which it is happening is very important here. So the program must have a couple of parameters which we understand from here. The first is that it should be able to control the robot, okay. So let's look at it this way. So the first requirement of the program is that it should be able to control, well, let's not use the word control, let's say it should be able to move the robot. It should be able to move the robot to perform some task, okay. The second thing the program should be able to do, it should be able to communicate, okay. That means it should be able to communicate between different machines. The part has come, part has gone. Then number 3 is part 3 would be that it should be able to avoid deadlock, or there should be no logic error, okay. This part is the most difficult, because for a program to find that out is extremely difficult. There can be other things like safety locks, there can be safety locks, okay, that if there are errors or there are suddenly something happens, it should be able to find out and stop the robot, okay. So for a robot, the program, unlike a normal program, should be able to do all these features. It should be able to move the robot, it should be able to communicate with other machines, it should be able to avoid deadlock and logic errors, which is extremely difficult for the robot to self-diagnose that there is a fault somewhere. And last of all, it should be having safety features. So if, for example, if a human being has come in the vicinity of the robot, then the robot should immediately stop, okay. So that is a safety feature. So this is also, there would be some kind of sensors. So let's say there would be sensors like floor mats. So this floor mats will ensure that if a human being has come anywhere near, it immediately signals the robot and the robot stops, okay. So the program must be able to or the program should have all these functions apart from moving the robot. So we see that as the computer has got more powerful, the programs also have got more powerful, in the sense they can do more number of things. So first we have one program, one one computer, one machine, we have one computer, many machines, one computer, different kinds of machines with communication, logic, safety, etc. Then we have even more, that a computer is actually integrating with other functions of the industry. For example, not only is it doing spot welding, spray painting, it is doing other functions like material storage, material retrieval. Okay. So the full functions of the company or the industry are getting integrated. So the computer has become powerful and it can integrate all other functions of the company together. Okay. So this is essentially to show that this is the progress in which computer, not only the computer, so when I say computer I also mean the program, has progressed in terms of number of years. So this is about 1980s, 1990s is so late 19 or early 1990s is computer integrated manufacturing, where a computer could control all systems. Now we are talking about robot programming languages. So essentially we will see that robot system essentially consists of the mechanical hardware. It has arms, it has motion transmission, it has grippers. Okay. So a robotic system essentially would consist of mechanical hardware. Okay. Then there will be a robot control unit which has the robot controllers, okay, which is doing the actual PD or PID control, PD, PID or any other kind of control which it is doing. Then there are motors, there are actuators, there are sensors, there are power amplifiers, then there are ADCs and DACs. Okay. So the robot control units would consist of the robot controller, which is actually controlling the robot links through the motors, actuators and sensors. There will be power amplifiers to increase, because the controller would will not produce a very large current. So some of these motors will require very, very high current. So it can require from 1 ampere to 10 ampere currents. So this much of current cannot be given by a digital controller. So basically to get this kind of current we use power amplifiers to increase the current rating of the to increase the currents which are supplied to the motor. Okay. And then we have ADCs and ADCs. So ADC is analog to digital converters, we will see. Okay. So ADC is an analog to digital converter, and DAC, so this is an ADC, and DAC is a digital to analog converter. Okay. So this is a DAC. Now why are these two required? These two are required because when you are measuring any kind of, or you are using any kind of sensor, for example you are using a pressure sensor or a force sensor. So this sensor output is going to be analog in nature. So analog signal basically means it is continuous with respect to time. Okay. Now a digital computer cannot read on an analog signal straight. So it has to convert to a digital signal and then it is able to read. So if you are using a robot which is measuring the force that is acting at the end effector, so what it will do is it will use an ADC to convert the force signal to a digital signal, analog to digital, and then it can read the force signal. Okay. And the reverse of that is digital to analog conversion. If the robot has to now give a digital signal output to some other device, then it will have digital, sorry, it's the other way around. If it has to give an analog signal output to some device, then it can convert a digital signal, which is its own program output, convert it to analog and then give it. So this is basically used for communication. Okay. So communication with other machines, reading sensors, etc., etc. So the first part is the mechanical hardware, arms, motion, transmission. The second part is the robot control unit, and the third part is the central controller for interfacing robot with other machines. Okay. So the central controller is the one that will actually communicate with the robot control unit and will communicate with other machines. Okay. So for example the central controller will probably tell the robot controller to move in a particular to a particular location, position and orientation, and to the robot controller. The robot controller is the one that is going to actually enforce the motion that it has moved to the particular position and location. So a robot program, a robot structure, not a robot program, would consist of the hardware and the software. So these are essentially hardware components. Mechanical hardware are the mechanical part. This is the computer hardware. This is the control hardware, and this is the computer hardware. So these are all hardware and these are interconnected. Mechanical, electrical, computer science. Now essentially what we are seeing here is that for using a robot, we can teach a robot, or we can use a robot and teach it by using the teach pendant. Okay, that is one way, and the second is by using a program like a normal program we write. Okay, so in the teach pendant is something like the remote of a TV. So if a robot has 6 degrees of freedom, so let us say this is my robot, very simple example I am putting here. Okay, so this is joint 1, joint 2, joint 3. Okay, it has 3 degrees of freedom. So your teach pendant will be something like this, and it has a memory, and it has joint 1, joint 2, joint 3. It shows plus minus, plus minus, plus minus. Okay, so there is a joystick there. Okay, so using this teach pendant, which is something like a remote of a TV, what we can do, we can take this joystick and move it this side or this side. So what would happen is this particular joint will move like this, or it will move like this. Okay, and similarly I can toggle joint number 2 and move it this side or this side. Similarly I can move joint number 3 this side or this side. So manually I can take this the joystick and then toggle each of the joints and move it to the desired location. So if I want to move it here, then I can move it like this, and like this. So the robot has moved from there and it has come here. Okay, I can manually do that, and this is a manual process. So I am simply using the joystick and then moving the robot joint by joint. Now when it is moving, what it is doing is it is showing me the coordinates here. So x, y and z, and the angles theta 1. So in this case there is only 2, 1, 2, 3. So x, z and theta 1, theta 2. Okay. So the advantage of this is we are manually moving the robot from here to here, and when it is moving I can actually see that what is the position and orientation of the end effector as it is moving. Okay. So this is a manual, this is a process that is used to manually teach different points, and when it is being taught, what is happening, these points can be recorded in the memory of the robot. Okay. And once I have recorded these points, then I can play it back. So I am moving the robot from here to here, I record all the points by which it is going, and then I can play it back. So I can play it back as many number of times I want. Now the advantage of this is that it is very difficult to find points in space, the position and the orientation very accurately. Say for example, if I hold the pen here and I say at this tip, the tip of the pen here, okay, what is the position x, y, z? Now it has an x, y, z plus it has an angle. What are the 3 angles? It has this pen is making 3 angles with the 3 axes here, right? So in order to define the position and orientation of this pen, I actually need 6 parameters. I need x, y, z, plus I need the 3 angles alpha, beta, gamma that it is making with the x, y and z axis here. Now there is no sensor which will give you those 6 parameters, okay, because you can measure the distance from some origin, you can measure the distance, it gives x, y and z, it does not give those angles. Okay. So it is very difficult to find the position and orientation of a point in space. And so one way of doing it is by using a teach pendant and then taking it to the desired location and seeing in the computer memory where is this location, okay, position and orientation. So it has 2 functions. One is to manually teach, number 2 is to find out the points in space, position orientation of points in space. And there are special cases. So we will talk of special cases where there is where tasks requiring human skills are there. For example, what are the special cases? One is welding. Welding is a special case. Assembly is the other one. Okay. Then there can be other cases also. So when it is very difficult to teach a robot to do welding, let's say arc welding, mainly arc welding. Why? Because you would be knowing that when we do arc welding, the way the expert welder actually does, it's very difficult to mathematically record and write in the form of a program. So how is welding done? So the expert welder is going to touch the electrode onto the workpiece, then he will take it up a little bit, form the arc, and then he is going to move the arc in a particular fashion. And while he is moving, he also has to put, the electrode is getting consumed, so he has to move the electrode downward. Now to write that would mean find the position orientation at every point in that process would be extremely difficult. So what is done is that there is a teach pendant based teaching in which the expert welder will hold the welding gun and do the welding, and at every position and location during that weld the points are going to be recorded in space, and then it will be taught to the robot and the robot will play it back. So there is another example or another use of using a teach pendant. Okay. So teach pendant is for manually teaching, finding points in space, and for teaching jobs which require human skills. So the point here is human skills. okay, because human skills are very difficult to mathematically program in terms of a program. The second is program based control. So, in a program based control, a desired task is written as a sequence of motions, like in a program like in C language or basic language or Fortran. So, the desired task is written as a sequence of lines, okay, and the program executes line by line. So, in a program based control, the task is written as a sequence of motions in a language, say for example val language, and these motions are then played back. Okay. Now, in terms of robot programming, we have to remember that a robot will not do a task only once. Okay. For example, if I have to pick up an object from here and I have to put it here, then this task can be done in infinite ways. This trajectory can be like this trajectory can be like this trajectory can be like this. So, there are infinite trajectories possible, and the robot will not do it once. So, it will do it millions of cycles. So, what is required is the most time efficient trajectory, which is safe and which takes the shortest time, because we might say that if I take a trajectory like this and if I take a trajectory like this, the difference is only say 0.05 seconds, but 0.05 seconds into 10 million cycles is actually a very large number. So, even if there is a difference of a fraction of a second somewhere, okay, if you multiply that into millions of cycles, what you get is a very large number. So, the robot program should be such that it can do the task in the shortest possible time. Okay. So, this is something very, very important and something to remember. So, we have seen there are two ways of programming. One is teach pendant based, the other is program based control. Now, like the full robotics in the past, robotics was also divided into 3 generations. We had first generation, second generation, third generation robots. Today we have the present day and the future robots. So, similarly this programming languages also evolved, okay, as robots also evolved, and so there are 3 generations of languages as of today. So, the first generation language is about 1950s to 60s. So, the first robots which are made use the first generation languages, and the first generation language essentially had simple commands for pick and place operations. For example, pick up this object from here, keep it here, and they had limited interaction with the world. So, they had limit switches basically for initialization, on off switches, okay, stops for end of work stage or work volume, but they had no interaction with the environment, no interaction with environment. Okay. What this basically means that it cannot interact in terms of force, torque, okay, say vision. Okay. So, there was no way this robot could actually interact with force sensors, torque sensors, inclination sensors, then vision systems, etc. So, there was no interaction with the environment. These were very simple systems which could simply pick and place objects, interact with on off switches, etc. Okay. So, this was about 1950s to about 1960s, and the early robots that were made were all run using the first generation languages. The second generation language is say from so this is about 1970s, so about 1970s or late 60s, so 1960s late to about here, we had what we call the second generation language, and this, the difference is that here we have interaction with the environment. Okay. So, this robots could interact with the environment by using force, touch, ADCs, vision cameras, etc., etc. Okay. So, second generation language is essentially robots which are smarter and which can interact more with the environment in terms of measuring force, touch, and that is because they had capabilities of ADCs, DSCs, vision processing, etc., etc. The third generation languages is what we have today. So, this is about from 1990s, okay, to about 1990s. Okay. So, let us see, this is about 50s to 70s, this is 70s to about 80s, and here we are about okay, 80s, and then after that we are in the case of third generation languages, or these are what we call intelligent languages. Okay. Intelligent languages are those which have the capability to understand general, let's say general human commands. Okay. So, here this is a computer program, this is a computer program, it has to be written like a program, but in the third generation language basically it is supposed to be some kind of intelligent language where it should be able to understand human commands. For example, if I want to pick up an object from here, suppose I have a pen here, I want to pick it up and I want to put it here, then the robot should be able to understand when it is being told that pick up the pen and put it here. The robot should be able to understand actually. Okay. So pick up the pen is English, it is not a computer language. It should be able to understand this command and generate a computer language which will actually execute the task. So that is what we mean by intelligent language, and this has been going on in the study of AI, machine intelligence, machine learning, and so many and so on. And from 1990s we have been people have been going on in this direction to develop more intelligent languages. Now the problem with the developing intelligent languages is that essentially when we talk of understanding human commands, so when we are trying to understand human commands, basically means that a human being can say different things in different ways, okay, or the human being can say something and mean something else completely, okay. So this intention of the command, intention of a human, or the context, is something a robot would find very, very difficult to interpret, and that is what makes this understanding of intelligent languages extremely difficult, okay. So there is a lot of work going on regarding intelligent languages, but not much progress has been made, essentially because it is very difficult for a machine to understand intention and context of what is being said. So example of a few languages that have been made. The first language that was started off in 1960s was called Victor's assembly language, and this was developed by the Unimation Corporation for the Puma robot. So the Puma robot means primary universal machine for assembly, and this is the basic Puma robot, so which was made around 1960s. So primary universal machine for assembly, and it was made around 1960, and the language is called VAL, or Victor's assembly language. The second language was developed by, and these languages are based on some computer programming language. For example, this one is based on BASIC, okay. So you know what is BASIC language. It was a very, very early and simple language. So the VAL language is based on the BASIC language, the structure I mean. The second language that was developed was AML, also around 1960s by IBM. So at that time IBM was manufacturing robots, and they developed this language AML for their robots, and of course IBM does not manufacture robots anymore, so this language is no more there, okay. The third language that was developed was RPL, and this RPL was also developed by several other companies for their robots, and this is based on the Fortran language, okay. Now also this is not there. So essentially most of the robots today would be using VAL, some derivative of VAL language, okay. And the VAL language essentially has a structure. So VAL language also progressed in terms of we have VAL 1, so we have VAL 1, then we have VAL 2, so we have VAL 2, and what we will be looking at in the subsequent lectures is how to program using VAL 2, and most of the robots around the world use some variation of VAL 2. The basic difference between VAL 1 and VAL 2 is that VAL 2 can interact with the environment. VAL 1 is a very simple language which only can take simple commands for pick and place, etc. So if you look at the structure of VAL language, then the basic structure of the VAL 2 language consists of these four parts. One is variables, constants, data objects, motion control commands, robot hand control commands, and program input output control commands. Now something to remember is that this is a basic language. It has the same structure of basic language, and if you look at the basic language, what it basically does is we have a line number, then you have a statement, then you have a line number again, you have a statement, and it executes sequentially from one statement to the other statement, and this is what we basically call the structure of the basic language. So the VAL 2 language essentially consists of these four parts, and in the next class what we will be doing is we will go through in detail about the structure of a program and then we are going to write a program to essentially show how it executes the robot. And then we have lab exercises where we have a Puma robot where we are going to actually show how the program is written and how the robot actually executes. So today we stop here and we'll continue in the subsequent classes. So thank you.